Very excited to be here. Thanks so much, Abby and Katrina. I am excited to speak with this cross-disciplinary community, especially. I think you both have done a fantastic job in organizing these and bringing together people who traditionally don't get to interact too closely, which is really kind of a theme of this talk that I want to get into. And I spent kind of a long time grappling with what the central thesis of this would be, specifically for this community. And what I kept coming back to was this convergence and the sensibility of convergence, which is something that I call antidisciplinary. And I'll talk a little bit about that later in the talk, but to build to it, I think one of the questions that helps do that is something that we don't ask seriously often enough, and that's why do we use machine learning for space science discovery? And my answer to this and my lead in to what I'll present as kind of a demonstrable example today is that it's useful and critical for kind of the wicked problems of our sciences. Those problems that have been really obstinate to progress, for which existing solutions have been inadequate, and those for which the problemscape that we see now requires new thinking. And so I think that those problems all require enhanced capacity. And so I'd like to suggest that these problems often represent areas that are at the boundaries between disciplines. And so that these are the areas that we need to use to converge. And we've heard a great deal lately, if you were part of the Helio 2050 conference and among these other workshops that are happening, about the need to understand systems science and the need to understand systems of systems. And so today I'd like to attempt to build a vision for that and kind of include a call to engage this liminal community in that vision. So I'm going to do that by demonstrating this for a specific use case, which I consider a wicked problem, and that's kind of particle transfer in the geospace system. But just throughout this talk, I wanted to kind of highlight a couple of different things that I think are really useful for machine learning applications. It's basically how do we build and continue to progress the solutions that we're providing. And I think we can do that in two ways. First, providing foundations to build on and usable artifacts. So anytime you see these icons throughout this presentation, it'll draw your attention to either a foundation that you can pick up and start building on, or something that's a usable artifact that can be beneficial to you. So I want to draw attention to those two things. So the problem that I want to talk about today is particle transfer in the geospace environment, particularly particle precipitation into the upper atmosphere from any given magnetosphere, and ion outflow, or particles that come from the upper atmosphere and move out into the magnetosphere. And together, these geospace particle transfer problems are key components to linking solar wind, ionosphere, magnetospheres, and really understanding the composition and dynamics of those regions. So these are very critical things, and I think it's very clear that geospace particle transfer is a grand challenge for geospace physics. And one of the reasons that it's a grand challenge is the complexity of the phenomena that are involved and the representations that our models that are required of our models to really achieve description of that complexity. So just to kind of very simply present what we're trying to do is often what we have are low Earth orbiting satellites that are observing these particles moving up and down into the upper atmosphere. And so we have these very local observations that we can stitch together. What we need is a high resolution global map that we can produce from those spatiotemporal observations. And so this is a wicked problem, as I call it. And I think I just put a link to a talk that Jesper Gerlov gave at CEDAR in 2016 that I think speaks wonderfully to this challenge. And I encourage you to go take a look at that. I'll post these slides for people after. But this is the same challenge that is faced by all magnetosphere-ionosphere coupling parameters, whether that's ion outflow, Poynting flux, electromagnetic fields, all these different things that we need to capture all kind of have this same inherent challenge. So how do existing models handle this? Well, what's traditionally been done is we take these spatiotemporal observations and we compile many observations of these over long periods of time. And then maybe we add some driver or coordinating information, like the solar wind data, for instance. And then we put together this empirical estimate, or the statistical average of all of those observations. And in many cases, what we see here is kind of a picture like the Ovation prime model provides. And what I'm going to talk about specifically for this talk are particle precipitation models and observations. what we find as we have improved observations of the polar environment is that these models are missing some very key pieces of the environment that we really need to capture. And it's not just from a scientific understanding component, but we're also from the space weather and operational component, recognizing how important some of these small scale features are to the operation of our systems and the functioning of our society. And so really we need to start developing models that are capable of capturing some of these things. And I think in trying to figure out how we improve our models to do this and why it actually ends up being important to use machine learning, the really telling quote is from a review article that Pat Newell wrote in 2016, where he said that the most important aspect of an auroral precipitation model is the choice of the organizing parameter. And so I think that that really pushes us to think that the improvements are going to require to expand the organizing parameters and find more expressive representations of that information. And so I wanted to outline this problem in a very specific way. And I chose to frame it as one of information representations for two reasons that will be the central themes of this talk. The first is that because it is a useful way to think about why and how we use machine learning for science. And then two, I think it's the bridge that leads to the broader point that I want to make, which is to consider how we structure our information so that it is usable and discoverable, and ultimately so that it can allow our progress to build on itself and to connect our different myriad communities, groups, and projects. And so basically what we have to do is take these organizing parameters, our state descriptors and our drivers of these phenomena, and we have to figure out how to represent this information so that we can produce this map that we want to get. So how do we set this up? How do we actually do this in this application? The first step is the data integration. So we look at our data landscape, which includes solar wind data. It includes data from throughout the magnetosphere, and then it includes these low Earth orbiting observations. For this case, we're going to be using the DMSP, or Defense Meteorological Satellite Program data. And we organize those, we align those, we clean them up, and we put them into a form that can be used for machine learning. So one of the things that you'll find as a usable artifact from this is we've published the database of many years of DMSP data that we've made AI ready, so that people can pick those up and start to explore with them. One thing that I do not have time to get into today, but that we do go into detail with in the paper, and that is critical for any machine learning application, is that it's very important that you understand the representativeness of your data, both where it is representative of what you're trying to do and where it's not representative. So you need to understand the limitations of the database that you provide and you produce. I'll point you to figure 2 in the paper that we published on this to show how we explore the representativeness of those data. But the second part of this setup is data representation. Why are we going to use machine learning? I've already talked about the choice of organizing parameter being really important. And the reason for that is that when we have complexity between the input and output, sometimes a higher dimensional relationship is required than, say, the empirical models that exist now. And machine learning models can help do that. It provides an algorithmic means to incorporate higher dimensional input parameter spaces and create models with greater expressive power. And so that's really what's pushing us to use machine learning for this, and when it's appropriate to use for science. So how do we go about understanding, training a model, building models, and understanding whether those models are doing what we need them to do for applications for these wicked problems? So one of the things that's important, I'm not going to get into the building of our model architecture. This is a deep neural network that we've designed. Happy to talk details about that with people offline or point you to the paper. But I want to talk about some of how we actually understand what the model's doing, which I think is important. So during training, I think it's very important to observe the learning process, witness how the model is actually developing a better representation of the data. So what I'm showing here are mean absolute error and mean squared error across the training and testing data. So train in blue, test in orange. Standard split of the data. The test data are not shown to the model as it's training. And it's basically going to tell us how the model is doing over time as we train it over these different epochs. So another way that we quantify this as we're looking at this during training is the histogram of these test data. So basically, these are the DMSP observations that we're testing over. And one thing I want to point out is that we have a bimodal nature in the distribution. And what that's pointing to is that the DMSP data contain the complexity of the geospace system, where we have kind of this multimodal or different systems impressing themselves upon the data. And our machine learning model needs to be able to model that complexity if it's actually doing something that we need. And so what I do here is I look at how the model represents the data over time. And so we look at the very first epoch, the first look at the training. What you see is that after this first epoch, the model is really just finding the geometric mean of this distribution. And it's just saying, here's the nice average that we're finding here. And really this is something that the empirical models are doing as well. They're just kind of finding the average and smoothing out this complexity. But as we look over time, we actually able to see across epochs, our learning process is actually starting to capture some of this inherent complexity in the data and doing a much better job of representing that. Then you can actually also understand when the model is no longer sensitive to new information or that it's exhausted the information that exists in the database you provided it. At this point, if you want to improve, you need to think about what new information needs to be passed to the model. And you've reached kind of the extent of what you've been able to learn from this. So a few of the lessons in observing this learning process is it's very important, and you can generate a lot of traceability in how your model's doing while observing the learning process. And then also the importance of starting well. If we were able to start at a epoch where we weren't just predicting the geomagnetic mean, we can more rapidly converge on something that is more representative of the problem. So we trained this model over 50 plus satellite years of DMSP data. And we wanted to understand how well it does. And so I think that one of the usable artifacts from this, one of the very important things is we developed what we think is a framework for evaluating these models. And we build that across 3 different levels. The first is the very standard metrics that we use. And in this is important to use a spectrum of metrics that I'll talk about in a moment. Then go into how does it measure up against what exists now and what the state of the art is now. And then to actually examine it over known geophysical phenomenon. And so I'll step through how we do each of these for this particular model. So the model we developed, we've labeled PrecipNet. And over the standard metrics, basically what I'm showing here is over all of our validation data, which is from the DMSP F16 satellite for all of 2010. So that represents over 50,000 data samples and over 1,500 satellite passes. So this is a pretty representative data set here. And we're going to compare with Ovation Prime, which is considered state of the art for this. So basically what I'm showing here is the histogram of the flux of the model prediction versus the actual observation. And I'm doing that for our model and Ovation here. And you see that our model is much better falling on this one-to-one line where it's very accurately representing the data. And you can again see this bimodal distribution of the data, which has been explored, is a characteristic of the data that's been explored. What you can see from Ovation is that there's actually a large degree of overprediction that's happening here, especially at low flux values. And what that means is that it's kind of spreading that information using that representation. And we need to do a better job than that. This is a histogram. If you take all of these data and put them on the histogram, you can see again that the PrecipNet model in green here is doing a much better job of capturing those data. So you can take all those and you can produce these summative metrics. What I've put together this table, which is largely benefiting from the work that Mike Lamone has done in 2018, where he outlines kind of the most useful metrics for geospace applications that must be examined. And so we've put those together and we evaluated the model as a first level of understanding the model's capability across those. And you can see here that the PrecipNet is improving upon Ovation Prime in all of these metrics. One thing I do like to point out is this R squared is actually the prediction efficiency. So basically that wraps both correlation and accuracy into the metric itself. And what you see is that Ovation actually has a negative prediction efficiency, which means that the mean value is actually doing a better job than what our state of the art is for these evaluation locations. And so we're providing significant improvement over that. And we're able to use tenfold cross-validation to get some uncertainty bounds of that. So that's the first level of evaluation. The second is to evaluate this against the state of the art. So we actually take realizations of the Ovation Prime model, which you see here as a polar view of what the Ovation model represents, take a pass of the validation data from DMSP F16, and we can plot the time series from that pass. We can interpolate the Ovation Prime model along that time series and compare them. And we can do the same thing for the PrecipNet model of this representative case. And what you can see here is one of the reasons why that prediction efficiency was negative for Ovation Prime. It's spreading that information. It's not really capturing these auroral dynamics very well, and it's kind of this averaged sense. But the machine learning model is actually doing a much better job of following those dynamics. We're still missing some of the mesoscale behavior, but we're starting to get significant improvement across that. And again, we do this for 1,500 satellite passes. We've looked at a large number of those, and this is really a characteristic of the data, of the results. It's doing a much better job. Then the final level is really to understand how this does over known geophysical phenomenon. Again, this is a usable artifact. We've published the model, a serialized version of the model, so you can pick it up and start playing with it on the GitHub that you see here, and love to interact with you and help you extend this work yourself. But basically, we've chosen a very nice geospace storm. This is a substorm that happens about the 1800 universal time location here. And it's preceded by this gradual increase and decrease in geomagnetic activity that allows us to understand if the auroral dynamics, if the auroral oval is expanding and contracting the way that we expect it to. And then when you get to this location, you're going to see an enhancement in the pre-midnight region that is kind of capturing some of the things we need to see from substorm specification. We chose this time, this is January 25th in 2000, because we actually have polar vis observations. And when we get to the substorm, you'll see those pop into the movie that I'm going to play here, in that you're actually going to capture some of the observations that the polar vis show us during this time. So again, this is PrecipNet. We're looking at the full global realization of that model. We're looking at ovation prime here, and then we're actually plotting the auroral oval boundaries identified by each of the models. And so you can see that we're moving towards quiet period here. The PrecipNet model's contracting the auroral oval as it expects, and it's moving to higher latitudes. So it's following that known physical phenomenon. The ovation model is relatively insensitive to that. So it is spreading that information. And here come the polar vis observations. You see the substorm go off there. And we're actually seeing some of those activations that happen in the pre-midnight region here in the PrecipNet model. So it's really exciting that it's able to start capturing some of those things. And I think it's doing a pretty nice job there. So that's the third level of evaluation. But a key question in any machine learning application is, how does the model improve, and does the model improve if we increase the complexity of the model? So a lot of times you'll see people just add hidden layers, move to more complex model representations, but we need to understand, is the performance actually commensurate with that added complexity? And so that's where we've gone next. So basically what I want to say is, if I add different machine learning model realizations here, would I see improvement with the increased model capacity and complexity? And so we started to explore that. This is the next paper that we're working on. It's a follow-on to the one that is the work that I just presented. And a few things that we're really excited about. And I think these are foundations that people can use. One of the things I think is going to be really critical for our field moving forward is loss function engineering. Any machine learning problem is going to produce some solution. It's going to optimize for something. But we need to be very careful about what we're optimizing for, so that we actually end up with the models that are giving us what we need. So I think Francois Chollet has voiced this well about the importance of loss function engineering. For this application, we've designed a new tail loss function that has been tailored from the machine learning literature to penalize, add additional penalties for higher flux observations. So basically, the more intense the precipitation, we want to penalize if the model is missing those. So it pushes it to really capture that. So we designed this new tail loss function that I'm happy to talk more with people offline. The second area that I'm really excited about is multitask learning. So if you think about how humans learn, basically we don't do individual tasks in isolation of one another, as rather we use auxiliary tasks to add on learning in how we interact with the world. And so one of the ways that we're kind of tailoring that to this environment is we're doing a multitask learning problem where the first task is to predict the auroral region, a simple classification model between subauroral, auroral, and polar regions. And then in each of those classifications, we can do different predictions to produce a new regression map and see how well that improves. And then finally, we're trying to take advantage of the spatiotemporal information at one time for this model, and actually doing a 2D spacecraft model, 2D transpose model that predicts the whole global map at one time, rather than predicting an individual location that we then have to evaluate the model at all locations to do. And so basically what I've done here is rather than get into the details of those in the limited time today, I just kind of showed, I selected a very critical time during this event I already presented, and I'm showing the state of the practice, this ovation prime. the new state of the art, which we're calling our precip model. And now I'm advancing those with these tail loss and the 2D conv model. So basically these represent increasing the complexity of the modeling technique. And we're actually very excited about some of the things we're seeing here. So basically it's the tail loss is better capturing some of the information in this midnight region. And we're actually starting to see some more mesoscale activity emerge in the 2D conv model. I won't go into too much more detail of those here in this talk today, because I do want to speak kind of more broadly about some of the things that I think this work illustrates, and that will be useful to this group. I think that Abby and Katrina have done a really outstanding job of bringing this multidisciplinary group together. And so I think you've been witnessing a lot of advances in machine learning. I think the questions we face now are these threshold questions of how do we converge these applications, which come from across heliophysics and planetary science and astrophysics, and how do we connect the artifacts and the usable artifacts that are coming out of them? And then finally, how do we link the individuals in the groups that are working across these? And I believe, and what we're working on now, is that the answer is in knowledge graphs. And so I want to talk just very briefly about knowledge graphs. I think the key question is, how are we structuring our data? How are we representing our information? And how is that representation serving or not serving us? And my response to that is that the relationships between the data that we are using are critical for usability and discoverability, and also for new capacities for those data. And so I think anytime relationships are important, we should be thinking about graph structures for those data, or basically representing objects as nodes and their relationships as edges between those nodes. I think we need to look no further than the internet to understand the power of linking data and the graph structure. So basically, if you look at what I'm showing here, this is Wikiverse. It's a representation in graph format of what's basically going on in the back end when you interact with Wikipedia. So we can either navigate via pages like we're used to on the internet, but on the back end, what's happening is we're moving through this vast knowledge network that's been produced for the internet. And the question is, what if we had this for space physics? And that's the question that's motivating this new project that's funded through NASA called the NASA Early Career Investigator Program, called Heliophysics Knowledge Network, or Heliono. And what we're trying to do with Heliono is provide the structure that allowed us to develop the precip model, for instance. Take the information across the heliophysics system and actually make these relationships first-class citizens, and actually provide those relationships so that people can navigate them and more easily access them. And so Heliono is the collection of software and systems for improved information representation in heliophysics. And it's also meant to be a digital commons for the community to use and coordinate through them. And so I think that this is us moving towards that for the heliophysics community. But I think if you think about this ML4PSP group, this can be applied and actually help link across all science directorates. And so I think a question that we often face and that we can address with this relationship, this graph structure, is we're all immersed in a number of different projects, all these different groups, different presentations, conferences, and organizations that are going on across our community. How do we track these connections, and how do we come together so that we're not reinventing things, but we're actually we're able to discover what's out there and do that in a fully searchable way? And so I think to better understand these resources across our community, this knowledge graph structure is really exciting. So I know I'm at the end of the time here, so I prepared a few broader points for discussion orientation, and happy to throw these up whenever we have the moment for discussion. But thank you again for the opportunity to talk with everyone today. Looking forward to hearing what people's thoughts are.